Hello and welcome to our presentation, a special case of a two-stage model of Lewis and Li. My name is Ted Mokantine and I am here with my research partner Logan Urquhart. Our research faculty mentors for this project are Tim Pervanecki and Professor Serena. This video is being recorded on April 13th, 2021 for the 2021 UW-Eau Claire Math Retreat. In their 2012 article, Spreading Speed, Traveling Waves, and Minimal Domain Size in Impulsive Reaction Diffusion Models, Mark Lewis and Bingtuan Li analyzed the following equation. The partial derivative of du dt equals d, the second partial derivative of u divided by x squared plus alpha u minus gamma u squared. This equation was used to analyze a population model that has a seasonal birth phase and a seasonal dispersal phase. In other words, during the first part of the year, the population decreases due to predators and natural causes, while during the second part of the year, the population reproduces and increases. In this equation, d represents the population diffusion across the spatial component. Alpha, as a real number, describes the natural growth or death rate. Gamma, as a positive real number, describes the effect of competition in the environment. X sub n denotes the number of individuals at the beginning of the reproductive stage in the nth year. G of x sub n models the between-season dynamics of the population, and U models the within-season dynamics of the population with a time and spatial component. The following assumptions were put on the model analyzed by Lewis and Li. First, alpha is a real number and gamma is a positive real number. G of x is a continuous function for x greater than or equal to 0. G of 0 is equal to 0. G prime of 0 is greater than 0. G of x is greater than 0 for all x greater than 0, and g of x divided by x is non-increasing for x greater than 0. At the beginning of their paper, Lewis and Li briefly mentioned that if we let d equal 0, then individuals do not diffuse and the population dynamics are described by du dt equals alpha u minus gamma u squared. This equation can be simplified to the following equations. Note that we split the equation up into two cases, the case when alpha is 0 and the case when alpha is not 0. Finally, by taking this equation out of recursive form, we are left with these equations. These equations were labeled as equation 3 and equation 4 in the paper by Lewis and Li, and we will refer to these equations by these names for the remainder of the presentation. Lewis and Li did not expand upon equations 3 and 4 in their paper, as they were more concerned with the application when the diffusion constant d is not equal to 0. But when d equals 0, they did mention that if g prime of 0 times e to the alpha is greater than 1, then a positive equilibrium solution exists. This idea led us to our research goals. Our first research goal was to identify positive equilibrium solutions and their stability in equations 3 and 4 for several g of x functions that meet the assumptions outlined by Lewis and Li. Our second research goal was to analyze g of x functions that dropped certain assumptions that were outlined by Lewis and Li, and to see if we could still find these equilibrium solutions. Before we continue with the results of our research, let us first remind ourselves the basic definition of equilibrium solutions. Given a model of the form x sub n plus 1 equals f of xn, x star is an equilibrium solution or fixed point of the model if and only if f of x star is equal to x star. If x star is a fixed point of a dynamical system, x sub n plus 1 equals f of xn, then x star is locally stable or attracting if the absolute value of the derivative at x star is less than 1, and unstable or repelling if the absolute value of the derivative at x star is greater than 1. The first function we analyzed for g of x was the linear function, g of x equals ax, where a is greater than 0. In this case, equation 4 becomes f of x equals ax divided by a times gamma times x plus 1. After a bit of algebraic manipulation, we find that the fixed points of the system are x equals 0 and x equals a minus 1 divided by a times gamma. After some more algebraic analysis, we find that x equals 0 is a stable when a exists between 0 and 1, and unstable when a exists between 1 and infinity. While x equals a minus 1 divided by a times gamma is stable when a exists between 1 and infinity, and is unstable when a exists between 0 and 1. We created a visual bifurcation diagram to represent our findings. This slide shows the bifurcation with several different values of gamma. Substituting ax in for g of x in equation 3 holds a very similar process. In this case, the f of x function becomes as is shown on the slide here. Once again, we perform algebraic calculations to find that the fixed points are x equals 0 and x equals alpha a e to the alpha minus alpha all over gamma multiplied by the quantity e to the alpha times a minus a. If x equals 0, for x is equal to 0, we have a stable critical point when a e to the alpha exists between 0 and 1, and an unstable critical point when a e to the alpha exists between 1 and infinity. Furthermore, alpha a e to the alpha minus alpha divided by gamma e to the alpha a minus a is stable when a e to the alpha exists between 1 and infinity, and unstable when a e to the alpha exists between 0 and 1. And here is our bifurcation diagram for this case. And with that, I will hand the presentation over to my research partner, Logan.
The second equation that we used for g of x was the Beverton-Hole model, which is defined as r of x all over 1 plus x, where r is greater than 0. Substituting this model in for g of x in equation 4 gives us f of x is equal to r of x over gamma times r times x plus 1. Once again, we perform algebraic calculations and find that the fixed points for this are x equals 0 and x is equal to r minus 1 over gamma r plus 1. X equals 0 is stable when r is between 0 and 1, and unstable when r is between 1 and infinity. X equals r minus 1 over gamma r plus 1 is stable when r is between 1 and infinity, and unstable when r is between 0 and 1. Here's the bifurcation diagram for that. Substituting this in for g of x in equation 3 holds a very similar process. In this case, f of x becomes the function that's defined on the screen. Once again, after we performed algebraic calculations, we found that the fixed points for this are x equals 0 and x is equal to alpha r e to the alpha minus alpha all over gamma r e to the alpha minus gamma r plus alpha. We find that x equals 0 is stable when r e to the alpha is between 0 and 1, and unstable when r e to the alpha is between 1 and infinity. We find that our other fixed point is stable when r e to the alpha is between 1 and infinity, and unstable when r e to the alpha is between 0 and 1. Here's the bifurcation diagram of Beverton-Hole composited into equation 3. Having analyzed several g of x functions, we now decided to analyze how dropping some of these assumptions might impact our findings. The original assumptions of g of x, as outlined by Lewis and Li, are shown on the screen. For this portion of our research, we modified the assumption that g prime of 0 is greater than 0, changing it to g prime of 0 is equal to 0. In dropping this assumption, we can no longer use Lewis and Li's findings that if g prime of 0 times e to the alpha is greater than 1, then a positive equilibrium exists. Past research has shown that many models with g prime of 0 equals 0 have Ali effect. Thus, to find suitable g functions, we first analyzed several common functions to see if they have Ali effect when composited into our equations 3 and 4. A function f of x is said to have Ali effect if f double prime of 0 is greater than 0. Furthermore, the Ali effect is considered to be strong if f prime of 0 is less than 1. Also holds for f of x. Based on the previously given definition of Ali effect, we found that equation 4, f of x equals g of x over gamma g of x plus 1 has Ali effect if g double prime of 0 is greater than 2 gamma times g prime of 0 squared. Furthermore, the Ali effect on this model is strong if g prime of 0 is less than 1. We then do the same thing for equation 3 and find that equation 3 has Ali effect if g double prime of 0 is greater than 2 gamma g prime of 0 squared times 1 minus e to the negative alpha over ae to the negative alpha. Furthermore, the Ali effect is strong if g prime of 0 is less than e to the negative alpha. Equations 5 and 6, as shown on the screen, are two examples of growth functions that meet most, but not all, of Lewis and Li's assumptions. When composited with equations 3 and 4, by serving as the g of x function, these equations have Ali effect for certain values of a1, a2, a3, and a4. These functions came from a paper by Dr. Hannah Escala and Dr. Kali Pavernav titled The Ali Effect in Mechanistic Models Based on Inter-Individual Interaction Processes. Because equations 5 and 6 were too nonlinear to solve by hand, we generated the following bifurcation diagrams in MATLAB. This is growth function 5 composited into equation 4. Here's growth function 5, as previously mentioned, composited onto equation 3. Here's growth function 6, as previously mentioned, composited onto equation 4. Support for this project came from Student Blue Gold Commitment differential tuition funds through the University of Wisconsin-Eau Claire Student-Faculty Research Collaboration Program. Thank you so much for listening. Questions?